It's time for Lab 6 on our e-learning adventure. So we'll take a look first at starting on a review of what we're going to be studying in the lab and kind of the situation we're looking at here. So if I have a rotating disc like this that's spinning, and I have one like this that's at rest, and I drop them together, both discs will be rotating after the collision, but at a slower rate or a slower angular velocity. So this is exactly what we're looking at. As it turns out, this is essentially conservation of momentum, as we've been studying before, although it's conservation of angular momentum or rotational momentum. Let's take a look at how that works. For weeks now, we've been studying the fact that P equals mv, momentum equals mass times velocity. But in rotational physics, angular momentum is known as L. Instead of mass, we have something called moment of inertia. A quick point about that, as you've learned in lecture already, hopefully, that the distribution of mass matters. When there's more mass concentrated toward the edge of the object, it's got more inertia. It's harder to get going or harder to stop once it's moving. And so we have to take into account not only the mass of the object, but also the shape of the mass. That's why moment of inertia is not just a set value. Also, we have velocity, which is now an angular velocity. It's measured in radians per second. Moving right along, we can see that, of course, momentum is conserved in the lecture class and in lab. So here we're going to try to show that and prove that with this lab. Essentially, if we add up all the momentum before, they should be equal to the momentum after. I want to translate this into the little example that I just showed you. Initially, we only have one rotating object with angular momentum, but at the end, we have two rotating objects, each with their own moment of inertia. If we factor out the final omega, because it's the same for both objects, as they're moving as one, we get this statement. I1 plus I2 is I final. So the sum of the rotating objects' moments of inertia is the final moment of inertia. So let's move on for just a second into a couple more specifics of what we're going to be doing today. Okay, so what we have here is the vernier software, and you can see quite simply, it records angular velocity. It records the fact that that disc that was rotating at the beginning at a certain angular velocity slowed way down once that disc came in contact with it. So we have an initial angular velocity and a final angular velocity. Those values are going to be critical. So what I've done is I've done for the first portion of the lab, I've done 5 trials with that collision you just saw in the last video segment, and I've exported that data into Excel for you to work with during this lab. And here is that data. You can see that there's 5 separate trials that I've given you here. Critically in yellow, I have highlighted where the collision is occurring. You're going to be asked to come up with your own method to determine the initial angular velocity and the final angular velocity. But you need to be careful not to use the data where the collision was occurring, because we've got some sliding and some friction going on there. We really are interested in just the initial and the final values. So there's a variety of methods you could use. I'll leave that up to your own scientific discretion, because that's one of the questions you'll need to answer and write about on the lab report. From there, you'll move on to the disk calculations tab at the bottom. So here is where you will actually input the results of your trials, the angular velocity and other provided information, to show whether or not angular momentum was conserved. Again, the whole point of this template that you're provided is to show or not show that the angular momentum at the beginning was equal to the angular momentum at the end. As always, we'll calculate that delta, that change in angular momentum, and then obviously we would calculate a z-score at the end because the expected amount of change is 0. Okay, so here is where we kind of diverge from the planned experiment that we had. Because we're not here, we can't do some of the things we had planned. So after part D, as it says in the lab report, we're going to do something a little bit different, and I've included the instructions for that in the Excel spreadsheet as well as here in this video. So what we're going to do is take an unknown object, which I'll give you a nice close-up here. It's a plexiglass square emblazoned with Valpo physics that's been cut by our nice machine in the back behind this wall. And we're going to run the same type of experiment here by colliding this plexiglass square with this rotating aluminum disc. It's the same aluminum disc. This M1 is the same M1 that you used in the previous experiment. But here, we're colliding it not with a disc, a known moment of inertia. We're colliding it with this plexiglass square, which has an unknown moment of inertia. Our goal in the second part is to find I2 to solve for this unknown moment of inertia. Okay, we're going to use the data that I provide for one of the collisions, and also any Excel formulas that you're going to create to do this. So how does this work? Let me slide the computer over here a little bit, and you can see that. So there we go. As you can see, we still have just one rotating disk at the beginning. That's all we've got. So the initial momentum is easy to calculate, just as it was in the first experiment. But at the end, we have a sum of two moments of inertia. I1, we already know it's the same as in the first experiment. I2 is the unknown. They both spin together at some final angular velocity. We're going to do a little bit of algebra to solve for I2. So this fundamentally is what we're doing. We're going to try to calculate I2. That seems relatively straightforward, and it is in Excel. What gets a little challenging is the error propagation. Using the rules from the appendix for error propagation, we're able to derive this statement. How do you find the error on I2, the unknown moment of inertia, that moment of inertia of that plexiglass square, this thing? Well, it's a little complicated. We have an intermediate step. We need to calculate the error on this value first, which I've derived for you here. I would highly recommend making a cell in Excel that just calculates this, because that's complicated enough. Finally, to actually calculate the error on I2, the error on the moment of inertia of the unknown mass, we would take this value, plug it into here, which results in this formula. So here's how to calculate the unknown moment of inertia. Here is how to calculate the error on the unknown moment of inertia, I2. Finally, as promised, I've used the same Vernier software to gather some data, and I've provided that here for you in the tab called Unknown Object Raw Data. And then for part two, it's your job. We give you pretty much a blank slate here. This bottom tab called Unknown Object Calculations. It's your job to use the data you have, as well as the formulas that I showed you in the previous clip, to calculate I2 and the error on I2. In the lab report, I give you some hints as to how to calculate an expected value for this plexiglass square. And once you do that, you can compare that expected value to your calculated value and calculate a z-score and write about it, just like you know how to do from appendix page 8. Well, that's all I have for Lab 6. Good luck. We'll again host a help session here on Google Hangouts. If you guys have any questions, you can ask during that time, or you can always reach out to me on Google Hangouts, Google Meet, or by good old-fashioned email. Best wishes to you. Good luck. Let me know if you need any help.